All right, so let's just quickly talk about the memory interface for the 68,000. So I think we've already soldered the data bus on this thing right now. So it's probably a good time to talk about how the bus actually works, right? So here's what we're dealing with, right? So we got the 68,000. This is our processor, okay? And we're going to connect the processor to kind of two memories here, right? We have flash memory chip, which is in that big ZIF socket with the lever on it. And we have a RAM that's in the smaller socket, okay? And they're both going to share a data bus, and eventually we're going to add an address bus that's going to go to both of them too, okay? Okay, so we need to talk about how this stuff works though. Okay, so in the flash, first of all, we should talk about what the difference between flash and RAM is, right? So flash is non-volatile memory, okay? And basically what that means is that when you turn it off, when you unpower it, it is going to retain its contents, okay? RAM is called volatile memory, all right? And that means that you turn it off and it's going to forget everything, right? You turn it back on again and nothing's going to be retained from the last time you had it on, okay? So basically we're going to store our program in the flash, okay? And we're going to store our variables in the RAM. Perfect, okay? So now we want to talk about how does the microprocessor execute instructions and how does it read and write data out of the flash and RAM. Okay, so let's first just talk quickly about how it executes instructions. Okay, so all processors basically have the same process for executing instructions. Okay, so what they're going to do, the first thing they're going to do is they're going to fetch the instruction. Okay, so they're going to go out to memory and they're going to read the binary code from memory into some internal register in the CPU, and that's going to encode the instruction that's going to be executed. After they fetch the instruction, they're going to decode it, and that's kind of basically looking at that binary code and trying to figure out what is this instruction asking me to do. Okay? After we've decoded the instruction, we're going to execute it. Right? So that basically just means perform whatever operation the instruction is asking us to do. If it's an add instruction, we're going to add the two numbers that it's asking us to add. After we do the execute, we are going to access memory. Okay, and then finally we are going to update the registers. Doing that is called write back. Okay. So then what we're going to do is we're going to go through this whole 5-step process. Once we're finished with the last step, the write back, we're going to go back and we're going to go fetch the next instruction from memory. Okay, so let's talk about, we're going to kind of zoom in on this fetch operation now and talk about how do we actually access memory from the CPU. Okay, so remember memory is kind of a big table. And every row on the table has an index starting at 0. So 0, 1, 2, 3, 4. The index is called the address. Okay? And it has a data value in there, right? And the data value can be 1 byte. Okay? So what we want to do is when we're fetching an instruction, we need to know what address we need to fetch from. Okay? So we need to know what the current instruction is we're executing. That's going to be the address, right? And then the data that we're trying to fetch from that address is going to be read out from the memory. It's going to be supplied by the memory. Okay, this is called a read cycle. I'm going to read from memory. Okay, so here it goes, right? So first thing we'll do is the 68,000 is going to set up the address on the address bus. Okay, so the address bus is just a collection of about 20 wires, 20 or 24 wires. I think we're using 20 of the wires. And each wire is a different bit of the address, right? So we have a 20-bit address. 5 volts represents a 1, and 0 volts represents a 0. Okay, so we can have a 20-bit address with 20 individual address lines. The first thing the processor is going to do is the 68,000 is going to drive an address onto the address bus. Okay, and then it's going to use another signal called read-write-not to indicate that we're doing a read transfer. Okay, so there's two possible kinds of transfers, right? You can either read from memory or write to memory, right? So this wire here, this signal on the microprocessor, this read-write-not signal, is basically a way for the processor to signal whether it's doing a read from memory or a write to memory. So this will be a 1, 5 volts if we're doing a read to memory, read from memory, and it'll be a 0, 0 volts if we're doing a write to memory. Okay, so we're going to set up the read-write-not line. And then finally, once we've got the address and the read-write-not configured, we're going to assert this thing called address strobe. Okay, address strobe is a signal that the processor uses to tell the memory there is currently a valid address on the address bus. Okay, and this is kind of a weird signal because it's actually active low. Okay, so address strobe is true when it's a 0. Okay, so this is true value of address strobe, meaning that there's an active value on the address bus, and it's false when it's 1. Okay, I don't know why they do it this way, but all of the 68000's control signals are active low. Okay, so we're going to assert address strobe. As soon as the memory sees that we have asserted address strobe, it's going to look at the address on the address bus, and it's going to go look into its internal structure, its internal table, and it is going to respond by driving a data value onto the data bus. Okay, so the memory is going to drive the data value onto the data bus. Okay, and then once the data is stable on the data bus, the memory is going to assert another active low control signal called DTAC, data transfer acknowledge, and this is going to become active after there's a valid data value on the data bus. Okay, so if DTAC is 0, it means it's true, which means that there's a valid data value on the data bus. Okay, so once the processor sees that DTAC is asserted low, it's going to latch the data from the data bus, right? So the processor is going to latch it here. And it's going to invalidate the address strobe signal. And this, when the address strobe signal is invalidated, this signal is sort of like the end of the bus cycle. Okay, so once address strobe is invalidated, the memory will release the DTAC signal. The address on the address bus will become invalid. We'll put a new address on the address bus, and we'll start all over again. Okay, so it's like a six-step process. We assert an address on the address bus, and we set the read-write-not pin to be a read. We assert the address strobe signal low to indicate that there's a valid value on the address bus. The memory then drives the data onto the data bus. And then once the memory asserts that data onto the data bus, it's going to assert the DTAC signal, right? And that's a signal that tells the processor you can latch the data, it's valid. Okay. Once the processor's latched the data, it will release the address strobe signal, which is an indicator that we're done with the bus cycle, and then the memory will release the DTAC, and the 68K will release the address. Okay, and then we start over again. So there's a 6-step process here. Each one of those steps takes 1 clock cycle, right? Here, I should draw this like this. Perfect. Okay, so there's a 6-step six-step process where each step takes 1 clock cycle to complete. So in order to fetch a single byte of data from memory, it takes the processor 6 clock cycles, right? So for example, if we have an instruction that is, say, 6 bytes long, and we're trying to fetch it from memory, it's going to go through 6 of these read bus cycles, right? And each bus cycle takes 6 clocks, okay? So we have, if we're trying to fetch a 6-byte instruction, 6 bytes, it takes 6 clocks per byte. So that's 36 clock cycles to fetch a 6-byte instruction. Okay. And then once we fetch that 6-byte instruction, then we can proceed to decode it, which takes some clock cycles, to execute it, and so on. Okay. But just the fetch, just reading the instruction from memory, can take multiple bus cycles. And of course, since our data bus is only 8 bits wide, we can only fetch 1 byte at a time. If we had a wider data bus, if we had a 16-bit data bus, this would go a lot faster because we could get 2 bytes at a time. Okay, so that's a read cycle. The write cycle works pretty similarly, right? So a write cycle is basically where the 68K is going to write some data to memory. Okay, so it starts out pretty close, right? So the 68K is going to drive an address onto the address bus. It's going to use the read-write not line to indicate that we are writing to memory. So read-write not is going to be a 0 in this case to indicate that we're writing, right? And then we're also going to supply the data. So we're going to set the data up on the data bus. Okay, so the 68K sets these 3 signals up first, okay? And then once those signals are set up, then it's going to assert address strobe low, okay? Once address strobe is asserted low, that's an indicator to the memory that there's valid data on the data bus that should be latched, and we're doing a write, right? So we need to latch that data, right? So the memory is going to latch the data, and then once it's latched the data, it's going to assert the DTAC signal. Okay? Once DTAC is asserted, then the processor knows that the data has been latched by the memory, and it's okay to release the address strobe signal. Once the CPU releases the address strobe signal, the memory can release its DTAC, and the CPU can release the data, the read-write not, and the address. We can move on to the next cycle. Put a new address on the address bus, and then we may put new data onto the data bus, and whatever we need to do the next cycle. Okay? So this is a normal write cycle, right? Okay, so our goal in this video basically, now that we've already wired up the data bus, right? The data bus is 8 wires, right? And each wire is going to represent a single bit of information, right? So if we have 8 wires, we have 8 bits or 1 byte, right? So we've got 1 byte of data that we can transfer between the memory and the CPU, right? In this video, we're going to set up a couple more things. We're going to set up some more control signals, right? So we're going to set up the address strobe and the DTAC, okay? So what I just said here, I was just talking about all this stuff. I kind of lied to you a little bit about DTAC, right? I said that the memory is responsible for asserting the DTAC wire when the transfer has been complete, right? So in the write cycle, the memory will set DTAC low once we have latched the data into the memory. On a read cycle, it'll set DTAC low once the data is valid on the output of the memory, okay? That's not really true. Okay, so the memory is actually not able to assert DTAC itself, right? The way it works, right, is when we buy a memory chip, the memory chip comes with sort of like a specified delay time. Okay, so for example, in the memory that we bought, we have a 50 nanosecond input to output delay. So what that means is that here's my memory chip, okay? If I put an address on my address bus, okay, and I want to get the data out of the memory, right, there's going to be a 50 nanosecond delay between the time that I set the address on the address bus, the time that the address is stable on the address bus, and the time that the data is stable on the output of the data bus, okay? So there's actually no DTAC signal on this chip, right? We just need to make sure that as board designers, right, we actually need to create a circuit that sets DTAC appropriately, okay? So we actually need to build a circuit that's going to set the DTAC signal to a 0 after a 50 nanosecond delay from address strobe going low, okay? But it turns out, so we're actually using a 12 megahertz processor here, okay? So the 12 megahertz processor, the clock period on that is actually 83 nanoseconds, okay? Okay, so the clock period of our clock is actually longer than the delay time of the memory, okay? So what we can do here is we can actually hook address strobe directly up to DTAC, right? And so by the time that the processor asserts address strobe, on the very next clock cycle, it should be able to read the data out of the memory, if that's what it's going to do. Okay, so we're actually going to wire address strobe directly up to the DTAC signal, and the effect that that's going to have is basically that address strobe and DTAC are going to look the same. Okay, so if address strobe goes low, DTAC is going to go low right away. If address strobe goes high, DTAC is going to go high. Okay, and so basically the processor is going to assert address strobe, and on the following clock cycle, it's going to check to see if DTAC is low. It'll see that DTAC has gone low, and it'll just accept the data that's on the bus. Okay. The other thing you could do here is you could just wire DTAC directly to ground. Some people do that. That's also fine. We're not going to do that. We're going to use DTAC tied up to address strobe. Okay. If we had slow memory, so like let's say instead of 50 nanosecond memory, let's say we had 250 nanosecond memory. Right? Some memory is really slow, especially like older memories. Right? We're not going to be able to do this, right? We would have to actually have some kind of a delay circuit that waits 250 nanoseconds before it allows DTAC to go low, right? Because there's going to be a long delay between the address strobe low and the time when the data is actually available on the output, okay? So there's some ways you can build circuits that basically check and create this delay, right? We're not going to do that. It's too complicated. We just want to keep it simple here, so we'll just use some fancy memory that's really fast, and we'll just either ground DTAC or tie it directly to address strobe. Okay, there's a couple other signals that we're going to use that the CPU has on it. Right, it has these signals: bus request, which is active low, bus grant active low, and bus error, also active low. Okay. These are basically signals that are used. The bus error is used in case you have an error on the data bus. For example, let's say you try and write to a memory location that's in flash, right? You're not allowed to do that. If we detect that the program tried to write to a memory location that's read-only, then we could assert bus error low, and that could cause some handler to go and shut the program down or something like that. We're not going to do that. We're not going to support the bus error signal, so we're going to tie bus error directly to 5 volts in this design, okay? And there are going to be no bus errors in our design. Bus request and bus grant are used for situations where you have multiple CPUs that are both trying to access the same memory, okay? And the 68000 supports that, but we're not going to use multiple bus masters or multiple CPUs. We'll have the single CPU, and we're not going to use these pins either, so both of these guys are going to be tied directly to 5 volts, okay? And we need to make sure that these things are hooked up correctly in order for this circuit to work, okay? So the ultimate goal of this thing, after the end of this video, what we're going to do is we're going to hook the data bus of our 68000 up to all zeros, okay? So remember we have 2 buses. We have the address bus, and we have the data bus. Okay, so the address bus is an output of the 68000 to the memory, and the data bus is usually an input, right? Sometimes it can also be an output if the 68K is trying to write values out to memory, but usually it's an input. Okay, so what we're going to do is we're actually going to take this data bus, and all 8 wires, we're going to ground them. So we're going to hook them to 0, right? And what this is going to do is it's going to cause the 68K to interpret, every time it tries to fetch an instruction, the opcode that it's going to fetch is all zeros. Okay, it's going to get 8 zeros every time it tries to fetch an instruction. Okay, and this instruction is essentially kind of like a no-op. Okay, I don't think it's actually a no-op. It's a, I think it's like an and I 0 with D0. Okay, an and I. So it's not exactly a no-op, but essentially it doesn't do anything, okay? So basically, if we ground all of the data pins, it will cause the CPU to continuously execute this instruction over and over again, okay? Which is good for us because it's a good way of testing if our memory interface is working correctly, okay? So if we ground all of the data bus signals, we should see address strobe will go low for a second and then come back high, and then go low and come back high as it's fetching as it continues to fetch from different addresses in memory. Okay? And we should also see the detect signal. The detect signal is going to follow address strobe. Okay? And then the read-write not signal should be just a 1 the whole time, because it should only be reading from memory. This instruction is just going to keep executing this instruction over and over again, and so we're never going to be able to, we're never going to need to write to memory, so read-write not should stay high the whole time. Okay? So this is called free running the processor. Okay? And it just allows us to make sure that the clock is working, the power is working, etc. And so far so good. Okay, we don't need to hook up the address bus for this, right? We'll hook up the address bus later. We just want to hook up the data bus and ground the data bus. So that's what we're going to do here. We're going to hook up these control signals that allow us to just not take a bus error and not do bus requests and bus grants. Okay, and we're going to ground the data bus, and we should basically just see address strobe going up and down. That's going to indicate to us that our bus is hooked up correctly. All right, so let's solder the data bus of the 68,000. So what we're going to do, the data bus is going to be soldered with this blue wire. I've picked some special blue wire, real thin gauge. I think this is 30 gauge blue wire that I bought for this. You're going to want to use, I prefer using thinner gauge wire in general because it's just a little easier to work with. But, in particular for the address bus and the data bus, there's going to be so many of these lines running from place to place here that it's going to be a lot easier to work with small gauge wire. Okay, so I recommend using small gauge, 28 or 30 gauge is best. Okay, so basically what we're going to do is we're going to have we're going to have a line that goes from the 68K over to the flash, and then from the flash over to the RAM. All right, so we'll start with pin D0. D0 is going to be on pin 6. Yep, pin 6. So this is the top of the chip right here. So this is going to be the top here. So pin 6, let's see, here it goes, 10, 11, 8, 6. Starting from the left. So starting from this side of the board on the, let's see, I think it's on the inside. Let me just check here. Yep, on the inside. It's going to be pin 10, 11, 8, 6. That's D0 right there. All right. So I'll just connect it. There we go. That's real small. It's nice. So this is actually stranded wire. Stranded wire tends to be a little more difficult to work with because you kind of have to twist it so it doesn't get too frayed up once you strip it. But the nice thing about stranded wire is that it doesn't fatigue as easily as solid. So it's less prone to breaking off and stuff like that than solid is. All right. I've had on other projects, I'll be working on some part of it. You have to bend some wire out of the way, and then the wire will just break off. And you bend it out of the way because it gets over fatigued. And then you got to figure out, well, where did that wire come from? And then you spend an hour trying to fix some problem that you never would have had in the first place if the wire wouldn't have broken off. A stranded wire does that less. It'll still do it to some extent, but it's not as bad. Okay, so D0 on my flash chip is going to be pin 13. Okay. So that'll be, this is going to be pin 16, 15, 14, 13. Alrighty. So 16, 15, 14, 13 is right here. Okay. All right, so I'm gonna let's do something like this. Ooh, that doesn't want to cut. There we go. Okay. There we go. So here's pin 1 on the flash. Here's 16, 15, 14, 13. There's my pin 13. Okay. Might be a little too long. I don't know. Go a little shorter on that. Not sure what the best way to do this is. There we go. Right there. Okay, so I'm going to leave a little bit of slack on the data bus. All right, so 13, pin 13 on flash. Let's see here. So pin 13 on the RAM too. So I'm going to put both wires into pin, I'm going to try and put both wires into pin 13 here and hold them in place. And I'm going to solder it one time, hopefully. We'll see, I guess, how that goes. Without them falling out. Okay. It's actually a decent joint. So yeah, I put both wires, I kind of stuck them both into the hole there, and then I soldered them both together at one time. It'll be easier to do that than to solder one and then to try and solder the next one. Okay. All right, so this is going to be again 16, 15, 14, 13. There's my D0 on my RAM chip. We'll cut this guy a little long. And then may have to trim it, we'll see. Okay. So I encourage you to check, double check, triple check, quadruple check your pin numberings here, because if you screw it up, it'll be a hell of a time trying to find the problem. If you screw it up on a CAD tool, on a schematic, it's a whole lot easier to find your bug than it is if you screw it up on this board. So it's worth spending a little bit of extra time to be a little anal here. because ultimately it will save you a lot of time trying to find the bug. You know, if you screw up a cut, if you cross, let's say you cross two of your data wires, it's your chip, your board's not gonna do what you think it's supposed to be doing. It's not gonna boot, and you're gonna play hell trying to find the crossed wires. Okay. I just can't get this guy to. These wires or these conductors in this stranded cable are fraying on me here every time I stick it into the hole. Here we go. Okay, that's pin 13. Managed to get it in there. Now I'll just put a little solder joint on there, and hopefully it'll stick. Cool. All right, well, we got D0 hooked up. So we're only gonna solder D0 through D7. We're not gonna use the full 16-bit data bus. We're just gonna do 8 bits because it's just a lot fewer wires to solder. The other thing you want to do is you want to make sure that you don't short, you don't want to accidentally short two pins that are next to each other on the chip. You don't want to short two pins together next to each other. You can do that. Oops, see, I just did it right here. I don't know if you can see that. I just managed to short D0 and D1 together here with the solder blob right as I was talking about it. So you don't want to do that. That's bad. So I have this desoldering braid here that can be used to get rid of this stuff. And basically what it is it's just some copper, some braided copper, and you can kind of just heat it and it'll suck up additional, if you have an extra solder sitting around, it'll suck it up. There we go. Well, I kind of screwed the pooch on that too. Man alive. I'm not getting lucky today. Here we go. Let's see what we can do here. There we go. That's good. Okay. That looks good. Those are separated. They're not touching. You can use your voltmeter to check if they're touching each other. Okay, and then on the flash and on the RAM, it's called DQ1, that'll be pin 14. Okay, so it's going to be right above D0. Right, so that'll be right about there. So we'll just trim it about that long. Looks pretty good. Okay, so on my, whoops, I trimmed it for the going straight to the RAM. I want to go to the flash first. I'm going to trim it a little shorter now. Here we go, that's better. There we go, looks good. So this will be pin 16, 15, 14 is right here. Just twist those a little bit and put in the hole. I'm gonna put this bad boy in the hole here too. Nice. All right, we got them both in the same hole. And we'll just solder them together. Solder them in. Make sure we don't short the two posts next door to each other there. That looks pretty good. That's a decent joint. It's not shorted to anything. I think I'm... Alright, so my camera died while I was doing that, and I ended up just deciding to solder the data bus. So you can see I finished soldering the data bus there. I got all 8 wires hooked up from the CPU over the memory. And what I'm going to do now is I'm going to solder those control signals that I was talking about at the beginning of the video. Okay, so there's a few control signals that you need to pull high in order to make this thing work, right? So the end goal of this video is that we're going to free run the microprocessor, right? And you need to pull a few of these control signals high in order for the processor to free run, okay? So the one I'm working on right now, I think, is auto vector. It's called AVEC, auto vector, active low. It's on pin 24, I believe, 26, 25, 20, 23, pin 23 of the CPU, okay? So auto vector and bus error are going to be tied to 5 volts, but you can see I'm tying it to 5 volts through a 4.7 kilo ohm resistor. So I just put that 4.7K resistor in there, and I soldered it into the 5 volt bus on the end of the board. Right, and then what I'm going to do is I'm going to take a wire and I'm going to solder the other terminal of that resistor over to the AVEC wire on the CPU. Okay, there's my white wire I'm going to use. So basically, so I'm going to do that for the AVEC signal and for the bus error signal. Okay, so bus error, remember, when that's an input to the processor. Both of these are going to be inputs to the processor. Bus error active low is just going to tell the processor there was some kind of a problem communicating with the memory, and we need to run an exception handler to deal with it, probably just to shut the program down that caused the invalid memory reference. Okay. And then auto vector is basically a pin that's used for the interrupt handling. Okay, so we're going to bring auto vector low if we will have like an interrupt, say from like I'll say from the UART or something like that, right? We're going to get to that one later. We're not going to use that right now. Okay. Anyway, both of these signals need to be there and they need to be tied high in order for the CPU to run. Okay. But we don't want to tie them directly to 5 volts, okay? And the reason for that is that if we ever want to bring them low in the future, right? Let's say if we want to implement the bus error circuit in the future, if we want to implement interrupts from some peripheral devices in the future, then we don't want those pins to be tied directly to 5 volts. We want some way to be able to pull them up weakly to 5 volts so that we can pull them down to 0 volts. So that's why we're not tying them directly to 5 volts. Okay, so we'll use these resistors to hook the auto vector and the bus error signals up to 5 volts. And then I believe it's the bus request pin is also going to be hooked up. That'll be hooked up to 5 volts, but we don't need to have a resistor on that one. We'll just tie that one. We'll just wire that one directly to 5 volts. We don't need to tie it. All right, so now what we're going to do is we're going to hook up the reset circuit. Basically what this is we have a separate IC. It's a small package. It looks like a kind of a transistor package. It's just got 3 pins on it. It's called a DS1233D. Got that thing from Janko. Basically what it is, it's called a reset supervisor. So what it does is it just monitors the power supply, 5 volts. And it waits until the power supply reaches a minimum threshold to reset the processor. Okay, so typically what happens when you plug one of these computers into power is it takes a while for the power supply, for the 5 volt supply to ramp up from 0 up to 5 volts. Okay, and you don't want your processor trying to execute code or to start trying to execute code as that voltage on the power supply ramps up. Okay, so you want to make sure you have a stable power supply voltage at least say 4.9 volts or something like that before you allow the CPU to start executing code.
Okay, great. So we got all the control signals hooked up. We got the reset supervisor in there, and we are ready to run here. So we're gonna just try and free run this thing. Okay, so I said at the beginning that what free running is we're just gonna wire the data bus to 0 volts. Okay, so what I got, the way I'm gonna do that is I'm going to just plug wires into my zip sockets. So you can see here I cut a bunch of short lengths of that data bus wire. Okay, use whatever wire you want, doesn't matter. I have 9 of them here, right? 8 for each of the data bus signals, D0 through D7, and 1 for ground. Okay, so I am going to just stick each one of these data bus signals, each a wire into one of my data bus signals on my zip socket, and I'm going to put one wire into the ground input on my zip socket, and I'm just going to kind of twist them all together, right? And then basically what that's going to do, and I'll close the lever on the zip socket so to make good contact, right? And what that's going to do is it's just going to pull all of my data bus inputs down to ground, and that's going to cause the processor, every time it tries to fetch data from a memory location, there's not going to be any memory chips actually in here. It's just going to be fetching data, from a data bus that's just wired directly to ground. So it'll just read 0 every time it reads a location of memory. Okay, and as I said, I think I said at the beginning of the video that 0 is basically like a no-op signal. And what we're doing here in this free run is we're just checking to see if the clock is working and if the address generation is working and the bus cycles are working correctly. Okay, and the main thing we want to see here is that address strobes should be going up and down, and we should also be able to see that the individual address lines should be going up and down periodically. Okay, and we'll just use an oscilloscope to check that. Right, so
Okay, so I've got the CPU free running here, and I'm going to demonstrate that in a second. But I just wanted to say that I learned a couple of lessons from the free run. One of the problems I was having is that basically what was happening was I was testing the CPU by checking this pin here, which is address strobe, right? And address strobe should be pulsing as the CPU requests instructions from the memory, right? And as you see here, I've wired all of the wires on the data bus to 0. So we should be getting zeros on the data bus, and you can see that I've got address strobe pulsing here, which I'm happy about, okay? And it is pulsing at, let's see, 3 megahertz, right? Can we see that here? There it is right there. It's pulsing at 3 megahertz. So, all right, so that's good. What was happening before when I was doing this is I had wired up most of the bus signals on the chip. I think I wired up bus error, auto vector, and bus request. Okay, and so I had tied all of those either directly to 5 volts or through a resistor to 5 volts. They're all active low signals that cause an interrupt on the processor. Okay. And the CPU, when I would plug it in, the CPU would run for a couple of seconds, and then address strobe would just get stuck low, and it would just stay low. And then what I noticed was that I had forgotten to wire a couple of the other signals high. So it turns out that I had forgotten to wire bus grant acknowledge high, and I also had not wired halt high. Okay, so I think halt needs to be wired high. But I definitely forgot to wire bus grant acknowledge high, BG-ACK. It's pin 13. Okay, so as soon as I wired those 2 pins high, halt and bus grant acknowledge, then the address strobe just started working and the free running was working. Okay, so that's kind of the reason why we free run this thing, is just to make sure that we got all the all the signals working correctly. Okay.